We were looking at common types of continuous random variables. We started out talking about the exponential random variable. Now you want to talk about normal random variable. So let's start with notation. Now, x is said to be a normal random variable with two parameters mu, which represents the expected value of x, and sigma square, which represents the variance of x. And if sigma square is the variance of x, then we know sigma, which is the positive square root of variance, is the standard deviation of x. Now, when we talk about PDF of normal random variable, right, x which has two parameters, mu, which is the expected value of x, and sigma square, which is variance of x. Now, this PDF takes this form, and this is defined for values of x between minus infinity to infinity. So, normal random variable is defined for the entire real line, right? And this is the form its PDF takes. Here is mu, which is its expected value, and here is sigma square, which is its variance. Now we know, okay, we know continuous random variable takes on, and the sigma square is actually in the square root, right? So this is square root 2 pi sigma square. If you write it inside the square root, it's sigma square. If you write this outside the square root, then it will just be sigma, right? So you can write, so you'll see in the form of the PDF, you can either have the sigma square written inside the square root. If it's outside the square root, then instead of sigma square, you just have a sigma, right? Here it's inside the square. And we know continuous random variable takes on values where its PDF is non-zero, right? So in this case, a normal random variable takes on all values on the real line because its PDF is non-zero for all values minus infinity to infinity. Now, if we plot its PDF, then its PDF is going to be a bell-shaped curve, which is symmetric about its mean expected mu, right? So mu determines the center of the distribution, and sigma square determines the width of the bell curve. The higher the sigma square, the more wider the bell curve. So for a normal random variable, its parameters define its shape, right? Where mean determines its center. We can see both of these have the and sigma square determines the width, right? So basically, mean determines the center, the variance determines the width. Here we can see both of them have the same variance because they have the same spread, but they have different means. Here they have the same mean because as they have the same center, but the variances are different, right? With the wider one, i.e. distribution one has higher variance. Now, a special case of a standard. Now, special case of normal random variable is a standard normal random variable where its parameters mean is 0 and variance is 1. And the notation for standard normal random variable is that we often denote it by z. So z, which is normally distributed with mean 0 and variance 1, is called a standard normal random variable. And instead of f, which we typically use for CDF, we denote its CDF by phi, right? So phi of a is probability z is less than equal to a. So for standard normal random variable, we use z to denote it, and for its CDF, instead of the typical f, we use phi, right? So that's a special case of a normal random variable.